Good afternoon. I would like to announce, it's my pleasure for me to announce the next lecture of Tojeiro from Universidade Federal de São Carlos, entitled Genuine Deformations of Submanifolds.
Thank you, Jair. So one of the basic topics One of the basic topics in submanifold theory is to understand when an isometric immersion of a Riemannian manifold into Euclidean space fails to be unique. This is also one of the subjects to which Marcos has given significant contributions, so a substantial part of this talk is meant to survey on some of them. Of course, if we have an isometric immersion F of a Riemannian manifold into Euclidean space, one can produce infinitely many others just by composing F with a rigid motion of Euclidean space, that is, an isometry of Euclidean space. So when we talk about uniqueness, we should understand uniqueness up to this trivial equivalence relation. And the usual terminology for uniqueness in this sense is rigidity. So we say that F is rigid if any other isometric immersion of M into Euclidean space is given in this way. Otherwise, we say that it's isometrically deformable. And the same thing can be said for the conformal case, if we just replace rigid motions by conformal transformations of Euclidean space. That is, Möbius transformations. Well, in this talk, I will restrict myself to the case of Riemannian manifolds with dimension at least 3, the theory for surfaces being substantially different. Well, there is one case in which things are well understood with respect to this problem, and this is the case of hypersurfaces. The relevant geometric invariant related to isometric deformability of hypersurfaces is its rank, the rank of its second fundamental form, which is also called the type number of the hypersurface. In fact, one of the first results in this direction was obtained by Bies and Keeling in the 19th century. And they proved that any hypersurface which has type number at least 3 at every point is always rigid. On the other hand, any hypersurface which has type number at most 1 is flat by the Gauss equation. And so it's highly deformable, at least locally. And therefore, with respect to isometric deformability properties, the interesting hypersurfaces are those which have type number everywhere equal to 2. And those that are isometrically deformable within this class have been completely classified by Sbrana and Cartan in the beginning of last century. They proved that such hypersurfaces split into 4 distinct classes. First, we have the so-called surface-like hypersurfaces, which are just products of surfaces in R3 or cones over surfaces in the sphere, S3. And here, deformations of the hypersurface are given by deformations of the corresponding surfaces. Then we have the ruled hypersurfaces, which are those that admit one codimensional foliation by affine subspaces of Euclidean space. And these are also highly deformable essentially, the deformations are given by the smooth functions of one variable. But the most interesting classes of deformable hypersurfaces are the last two ones. Here we have hypersurfaces that admit precisely a one-parameter family of isometric deformations, like minimal hypersurfaces that admit associated families. And finally, there is this discrete type, which are those hypersurfaces that admit exactly one such deformation. But in fact, that hypersurface in this last class do exist was only established recently in a joint work with Marcos and Luis Florid. Well, in the global theory of isometric deformability of hypersurfaces, a fundamental result was obtained by Dajczer. He proved that a compact hypersurface of Euclidean space with dimension at least 3 cannot admit discrete deformations. And even these can only happen if the subset of totally geodesic points of the hypersurface disconnects it. A point is totally geodesic if its second fundamental form vanishes identically. So essentially, what Dajczer proved is that isometric deformations of a hypersurface can only be something like this. You consider this hypersurface, and its isometric deformation is given by keeping this part of the hypersurface fixed and reflecting the other part with respect to this hyperplane. This is a subset of totally geodesic points. Dajczer's result was later extended for complete hypersurfaces by Marcos and Detlef Gromov. They proved that if you have a complete hypersurface with dimension at least 3, and you assume that the hypersurface does not contain any open subset that is isometric to a Riemannian product of a Euclidean factor with an unbounded three-dimensional manifold, then it can only admit non-discrete isometric deformations along subsets that are ruled with complete rulings. This assumption on their theorem is related to a problem that, as far as I know, remains open. And this is the problem of deciding whether there exists a complete non-ruled deformable hypersurface in R4, which has type number everywhere equal to 2. This is unknown as far as I know. Well, let me make a brief digression to a topic which is closely related to isometric rigidity. Assume you have an intrinsic isometry of an Euclidean submanifold. The problem is whether this isometry extends to a rigid motion of Euclidean space that leaves the submanifold invariant. Well, it's easy to produce examples showing that this is in general not possible. But of course, it is possible if F is rigid. Just apply the definition of rigidity to the pair of isometric immersions F and F composed with G. But what's interesting is that for compact hypersurfaces of Euclidean space with dimension at least 3, rigidity is even not necessary as soon as we take G in the identity component of the isometric group of the manifold. So a more precise statement is the following. For a compact hypersurface of Euclidean space with dimension at least 3, the identity component of its isometric group always admits an orthogonal representation as a subgroup of the orthogonal group that leaves the submanifold invariant. Well, the local theory of conformally deformable hypersurfaces turns out to be completely similar to that of the isometric case. First, the rigidity result by Bies and Keeling has been extended to the conformal case by Cartan already in 1918. He proved that a hypersurface of Euclidean space that has dimension at least 5 is always conformally rigid if all of its principal curvatures have multiplicity less than n minus 2 at every point. And here again, hypersurfaces that admit a principal curvature of multiplicity at least n minus 1 are highly conformally deformable, at least locally, because they happen to be always conformally flat, that is, locally conformal to Euclidean space. So again, the interesting class of hypersurfaces are those which admit a principal curvature of multiplicity exactly equal to n minus 2. And Cartan also classified the conformally deformable hypersurfaces within this class. He proved, again, that there are these 4 distinct classes: the surface-like ones, the conformally ruled, which means that the hypersurface is foliated by open subsets of round spheres. And there are those that admit precisely a one-parameter family of deformations. And finally, those that admit exactly one such deformation. Well, in higher codimensions, the problem becomes much harder. The first result along this direction was obtained by Alan Derfer, who proved this extension of Bies-Keeling isometric rigidity theorem for hypersurfaces under a suitable extension of the number of type number. But I'm not going into details on this. But I should notice that this is not exactly a result that holds for any codimension, because this assumption imposes this restriction on the codimension. Alan Derfer's result was recently extended to the conformal case by Sérgio Silva, who was one of Marcos' PhD students. But in low codimensions, a much better result was obtained by Marcos and Manfredo by means of some invariants that they called the S-nullities and conformal S-nullities, respectively. Well, the S-nullity of an immersion is defined as this maximum dimension of the kernel of the orthogonal projection of the second fundamental form of the immersion onto an S-dimensional normal subspace. Maybe it's easier to look at the S-nullity in this way. It's the maximum dimension of a tangent subspace, which belongs to the kernel of the shape operator of the submanifold with respect to every normal direction in a certain S-dimensional normal subspace. So for S equal to P, this is just the usual relative nullity index of the submanifold. Well, the conformal S-nullity is defined in a similar way. It can be regarded as the maximal dimension of a tangent subspace for which one can find an S-dimensional normal subspace and a normal vector in this normal subspace such that the shape operator of the submanifold is this multiple of the identity for every normal vector in this subspace V. Of course, for P equal to 1, this is just the maximal multiplicity of a principal curvature of the hypersurface. So what they proved was these extensions of Bies-Keeling and Cartan rigidity theorems. More precisely, an immersion is isometrically rigid if its S nullities satisfy these inequalities for every S between 1 and the codimension. And here, a similar statement in the conformal case, with the S nullities replaced by the conformal S nullities. Well, let me give you a brief idea of the main tool in proving such results. And this is the theory of flat bilinear forms. So start with two isometric immersions of Riemannian manifold M into Euclidean spaces, which I will admit that have possibly different dimensions. Let alpha and alpha hat be their second fundamental forms, and consider on the direct sum of their normal bundles this inner product given in this way. Now define this symmetric bilinear form as the direct sum of the second fundamental forms of both isometric immersions. Then the Gauss equations for F and F hat just tell us that beta satisfies this equality at every point for every tangent vectors x, y, z, and t. Here, this is this inner product on the direct sum of the normal bundles. A bilinear form that satisfies such an equality is called flat with respect to this inner product. Flat bilinear forms have been introduced by John Moore as an extension of Cartan's theory of exteriorly orthogonal forms. And the main fact about flat bilinear form is this lemma, which in its most general form has been proved by Marcos and Manfredo, with later improvement by Marcos and Luis Florich. It states that if you have such a flat bilinear form, and we assume that the inner product on its target space satisfies this inequality, and moreover, if the subspace spanned by the image of beta is non-degenerate, then we have this inequality here between the dimension of this subspace and the dimension of the kernel of beta. Well, Marcos has conjectured for some time that the lemma would hold without this unpleasant assumption, but in fact that the conjecture was false was only established about 18 years later in a joint paper with Luis Florich. And of course, this is the condition that forces the restriction on the codimension in their rigidity theorems. Well, let me illustrate how one uses this lemma to prove rigidity results. So let us consider the simplest possible case, which is the case both f and f hat are hypersurfaces. That is the case p and q equal to 1. So in this case, if we assume, as in the B-scaling theorem, that the type number is at least 3, that is, that the second fundamental form has rank at least 3 at every point, then we get that this bilinear form beta has kernel of dimension at most n minus 2 at every point. And then, by the lemma, this implies that S of beta is degenerate. But here, being degenerate in a vector space is an inner product of dimension 2 just means that this subspace is spanned by the direct sum of two unit vectors n and n hat, unit normal vectors to f and f hat respectively. But then this equality that follows from this vector belonging to the orthogonal complement of this subspace just means that the shape operators of the hypersurfaces with respect to these two normal vectors coincide. And so the hypersurfaces are congruent by the fundamental theorem of hypersurfaces. Well, let me also indicate how one deals with conformal rigidity problems for submanifolds. For this, we use a model of Euclidean space as a hypersurface of the light cone in Lorentzian space. So we start with Lorentzian space of dimension n plus q plus 2, consider the light cone inside it, which is the subset of light-like vectors, and then we intersect the light cone with this degenerate affine hyperplane defined in this way for a fixed vector in the light cone. Maybe I do a rough picture here. So we fix a point, and what we obtain is a paraboloid inside the light cone. And it turns out that this paraboloid is a model for Euclidean space. The induced metric here is flat, is Euclidean. And in fact, one can produce an explicit isometric embedding of Euclidean space into Lorentzian space, whose image is this paraboloid. So the usefulness of this model for dealing with conformal rigidity problems is summarized by the following three facts. If we start with a conformal immersion into Euclidean space with conformal factor given by this function, this just means that the induced metric by f is phi squared times the metric of n. Then we can make it into an isometric immersion into the light cone in this way. We first compose it with this isometric embedding of Euclidean space as this paraboloid, and then we rescale the immersion with this factor, which is the inverse of the conformal factor. It's easy to see that in this way we get an isometric immersion into the light cone. And conversely, if we start with an isometric immersion into the light cone, whose image omits a certain generator of the light cone, then we can associate to it a conformal immersion into Euclidean space in this way, just by projecting it onto the paraboloidal model of Euclidean space. So we are just doing this. If we have a hypersurface here, we project it along the generators of the light cone onto this model of Euclidean space inside the light cone. And it turns out that two conformal immersions into Euclidean space are conformally congruent. This means that they differ by a conformal transformation of Euclidean space if and only if these isometric light cone representatives of them are isometrically congruent. That is, they differ by an orthogonal linear map of Lorentzian space. In this way, we reduce a problem on conformal deformation of a submanifold into a problem on an isometric deformation of its light cone representative, which should be an easier problem. Okay, but so far we haven't even touched on the really main problem on this subject, which is the problem of classifying which submanifolds of Euclidean space admit isometric or conformal deformations. Everything we have done so far was to know where to look such submanifolds. When we start to think about this problem, even in the simplest possible case, which is the case of codimension 2, we are led to the following basic observation. Assume we start with a hypersurface of Euclidean space of dimension n plus 2, which we call a Sbrana-Cartan hypersurface. This means that it admits another isometric immersion which is not congruent to the original, into Rn plus 2. Now consider any isometric embedding of a Riemannian manifold of dimension n into this Riemannian manifold n with dimension n plus 1. Then, if we compose capital F with this embedding J, we get an isometric immersion of M into Rn plus 2, which admits this isometric deformation F hat given by this composition. But of course, we should regard this isometric deformation of F as a non-genuine isometric deformation of it, because it's in fact induced by an isometric deformation of a hypersurface that contains it. Well, although we have already a very difficult problem to handle, we can make it still more difficult and general in this way. We can fix two integers, p and q. The first one we assume to be positive, but the other one can even be 0. And the problem is to classify all the isometric immersions into Rn plus p that admit isometric or conformal deformations in Rn plus q. That is, we can assume the deformation to take values in a possibly different Euclidean space than the original one. Observe that this problem makes sense even for q equal to 0. For instance, in the isometric case, this would reduce to classifying flat submanifolds in Rn plus p. And in the conformal case, making q equal to 0 in this problem is equivalent to classifying all conformally flat submanifolds of Rn plus p, because admitting a conformal deformation into Rn is the same as of being conformally flat. But a more illuminating example is the following. Assume we start with a standard umbilic inclusion of an open subset of the sphere into Euclidean space. Then one can, of course, produce infinitely many other isometric immersions of the sphere in Rn plus p just by composing this umbilic inclusion with any isometric immersion between the Euclidean spaces. We can think of this problem as, in a more geometric way as follows. You take a piece of a round sphere in an affine subspace in Euclidean space. Then one can obviously get isometric deformations of that piece of sphere just by deforming isometrically the affine subspace and then looking what happened to the sphere inside it. The problem is whether these are the only possible isometric deformations of that piece of sphere. In other words, is every isometric deformation of a piece of sphere in Euclidean space non-genuine? Non-genuine here means the deformation is in fact induced by the deformation of the affine subspace that contains it. Well, the answer turns out to be yes, at least on connected components of an open dense subset, until codimension n minus 2. N is the dimension of the sphere. But the answer is no for higher codimensions. And in fact, one can prove that the genuine isometric deformations of a piece of a round sphere in codimension n minus 1 are in fact in correspondence with the set of solutions of a certain system of PDEs that is called the generalized elliptic Sind-Gordon equations. And one can in fact produce explicit examples of such deformations by using the Hilbert transformation. Well, I think I can now try to drop the quotation marks in the word genuine and try to give precise definitions, which are due to Marcos and Luis. So, start with a pair of isometric immersions into Euclidean spaces with possibly different dimensions. Then we say that this pair extends isometrically if we can find an isometric embedding of the manifold M into a higher dimensional manifold, which admits isometric immersions into those Euclidean space in such a way that this diagram commutes. We say that F hat is a genuine isometric deformation of F if on no open subset it's given in this way. We also say in this case that the pair is a genuine pair. The same thing can be said for in the conformal case. Now, we say that F is genuinely isometrically readed if for any other given isometric immersion into Euclidean space, well, we have to fix this integer q. One can find an open dense subset such that on this subset, the isometric deformation is in fact given as in the previous diagram. So I hope to have convinced you that the correct problem in studying deformations, isometric and conformal deformations of submanifolds is to look for those submanifolds that admit genuine isometric or conformal deformations in a possibly different Euclidean space. And this problem was carefully studied by Marcos and Luis, and they observed that the relevant geometric property of a submanifold, in order that it admits genuine deformations, is being ruled. We say that an isometric immersion is ruled if it admits an integrable distribution whose leaves are affine subspaces of Euclidean space. Once we have a ruled submanifold, we must measure how far that distribution is from being relative nullity of the submanifold. And this can be done by this subspace, this normal subspace, which is the subspace which is spanned by these vectors, the second fundamental form applied to a pair of vectors, one of which in that tangent distribution. If this subspace is trivial, then D is part of the relative nullity of the submanifold. What they proved was that if you have a genuine isometric deformation of a submanifold and the codimensions of both isometric immersions satisfy these restrictions, then in fact both isometric immersions must be ruled with the same ruling. And they have also obtained a sharp estimate for the dimension of these rulings. And they showed furthermore that one has this strong relation between these two normal subbundles of the normal bundles of the submanifolds. Well, as a consequence of this theorem, it follows that we have that for a given isometric immersion in codimension P, if we choose any integer q satisfying this restriction, then F is automatically genuinely rigid in Rn plus q, unless it admits an open set which n minus p minus q ruled. In particular, if we start with a Riemannian manifold with positive Ricci curvature, then it's genuinely rigid in Rn plus q. Well, although this is quite a nice result, we are still very far from classifying submanifolds that admit genuine isometric deformations. The result just says where we have to look for those submanifolds. Well, let me give a rough idea on how one gets such a theorem. So let us start with two isometric immersions, as in the statement. What one has to do is to work hard to obtain a vector bundle isometry between two vector bundles of the submanifolds, satisfying these three restrictions. And they have proved that one can do that, and they also obtained this estimate on relating the dimension of D, the distribution, and the dimension of those normal subbundles. After one gets this, the remaining of the proof is easy, because one can show that this is exactly what one needs to produce isometric extensions of both isometric immersions. And it turns out that those isometric extensions are only trivial if the original immersions are ruled with that distribution D as the distribution of rulings. So if we assume that the original pair is a genuine isometric pair, then the extensions must be trivial. So we conclude that the original immersions must be ruled. And this is how they get their theorem. Well, in the last part of the talk, I will report on a recent work with Luis, in which we have, in particular, extended the theory of genuine isometric deformations to the conformal case. Well, in this case, the relevant geometric property of a submanifold is being conformally ruled, which means that the submanifold is foliated by rounds, open subsets of round spheres or affine subspaces. And again, we have to measure how far from being conformal nullity is this distribution. And this can be done by means of this bilinear form, which is defined in this way. Here, eta is this normal component of the mean curvature vector of the leaves of the distribution D. So if the subspace is trivial, it means that D is conformal nullity of the submanifold. In particular, if you have a hypersurface, the dimension of this subspace being trivial means that D is the eigenspace of a principal curvature of the hypersurface. So what we have been able to get was a completely similar version of their theorem for the case of isometric immersions. So assume you have a pair of conformal immersions that form a conformal genuine pair. In other words, F bar is a genuine conformal deformation of F. If we assume these restrictions on the codimensions of the conformal immersions, we can prove that they must be both conformally ruled with D as the common rulings of both submanifolds. And we have obtained a quite similar estimate for the dimensions of the rulings in terms of the dimensions of those normal subspaces. And again, a similar restriction on the relation between these bilinear forms in these normal subspaces holds. So as a corollary of the theorem, we obtain that a conformal immersion into Euclidean space is always genuinely conformally read in codimension Q if Q satisfies, besides those restrictions, this condition. F does not admit any open subset which is n minus p minus q conformally ruled. So to get a better understanding of the content of the theorem, let us look at some particular cases. Oops. So assume you have two hypersurfaces. Then if we apply that estimate, in this case, p and q equal to 1, we conclude that this integer must be 0. Otherwise, the right-hand side of this inequality would be negative. So this means that D is actually the eigenspace of a principal curvature of both hypersurfaces. So what we get is Cartan's conformal rigidity theorem. If we have a genuine conformal pair of hypersurfaces, both of them must carry a principal curvature of multiplicity at least n minus 2. If we apply the estimate for the case Q equal to 0, which means we are studying conformally flat submanifolds of Euclidean space, what we get is a result due to Moore, which proved this estimate on the conformal nullity of a conformally flat manifold, submanifold of Euclidean space. And he used this to study the topology of such a submanifold. Well, let me skip this one. But let me mention, this is one of the main applications of the theorem, is an extension of that conformal rigidity theorem I mentioned before by Marcos and Manfredo. So assume we have a conformal immersion into Euclidean space in codimension at most 5, and we choose any integers satisfying these inequalities. Then we assume these inequalities for the conformal less nullities, and notice that for p equal to q, they reduce to the inequalities in that result by Marcos and Manfredo. Well, if q is too big, we have to strengthen the assumption on the first conformal nullity. And what we conclude is that under these assumptions, any other conformal immersion of the manifold into Rn plus Q must be a composition of the original one with a conformal immersion between the Euclidean spaces. So, of course, for Q equal to P, this would be just a conformal transformation of Euclidean space, and this would reduce to Marcos and Manfredo conformal rigidity theorem. Oops. Well, another thing we tried to understand in this paper with Luis was the reason of why all results about isometric deformations of submanifolds has a similar counterpart in the conformal case. So, start with a Riemannian manifold of dimension n plus 1 that admits an isometric immersion into Euclidean space with codimension p, but also an isometric embedding into Lorentzian space with codimension q plus 2, which we assume that is an embedding that is transversal to the light cone of Lorentzian space. Now, consider the intersection of the image of this isometric embedding with the light cone. Call it M. Let me go to the other picture, which is better. Then we can produce an isometric immersion into Euclidean space just by this composition, and also a conformal immersion into Euclidean space of dimension n plus q that is produced in this way. Remember that when we restrict f hat to m, the image of this composition takes values in the light cone. Then we can project it into the light cone, and in this way we get a conformal immersion into Euclidean space of dimension n plus q. So what we proved is that in low codimensions, any genuine conformal pair in Euclidean space can be constructed in this way, starting from an isometric pair, a genuine isometric pair, taking values in Euclidean space and Lorentzian space respectively. So if you are already too tired, you do not need to read all these statements. It just says what I have just said. So some particular cases that can be illuminating. If we apply this fact to the case of hypersurface, what we get is that, roughly speaking, any hypersurface of Euclidean space that admits a genuine conformal deformation in Euclidean space of dimension n plus q can be locally produced as the intersection of a flat submanifold of Lorentzian space with the light cone. This is just because if we take p equal to 1, then this is just a local isometry. Then we can forget about this part and just assume we have an isometric immersion of an open subset of Euclidean space into Lorentzian space. They intersect with the light cone to produce the conformal deformation of F. Well, in the particular case where also Q is assumed to be equal to 1, this had been previously proved in a joint paper with Marcos. So every conformally deformable hypersurface of Euclidean space can be produced as the intersection of a flat submanifold of Lorentzian space in codimension 2 with the light cone. And this can be regarded as a non-parametric description of Cartan's conformally deformable hypersurfaces. Another particular case that is quite interesting is when we make Q equal to 0 in that diagram. So in this case, what we get is a construction of a way of constructing all conformally flat submanifolds of Euclidean space. All of them are constructed in this way. You start with an isometric immersion of a Riemannian manifold of dimension n plus 1 in Euclidean space that also admits an isometric immersion into Lorentzian space of dimension n plus 2. Then you intersect this submanifold with the light cone. This gives rise to the conformally flat submanifold of Rn plus p. And this was previously proved by Marcos and Luis in a paper in 1996. Well, let me give a brief outline of how one gets these results about genuine deformations of submanifolds. In the conformal case, one has first to extend the theory of isometric ruled extensions that had been developed by Marcos and Luis in the isometric case to the case of flat semi-Riemannian target spaces. Then we have to apply this extended theory to the isometric light cone representatives of the pair of conformal immersions that we start with. And then we have to go back and interpret the conclusions in terms of the original pair of conformal immersions. So now that we have an outline of the proofs, we can go to the detailed proofs. Thank you.
Question, please. No questions? Thank you very much.